Is it recorded local on the hard disk or
nella nube online? La nube, sì.
okay.
Tem um site dele.
Essa versante me tem um grande.
Tá aqui. Ó. Quando você vai clicar nessa página, né?
Isso.
Aí você vem aqui. Tá aqui. E aqui embaixo, né? Aqui.
Eu entrei e acho que eu não corri essa página. Obrigado.
All right, morning. How are you? Are you okay with me wearing a mask or should I wear it?
Não,
Are you okay? So, two things. First of all, someone you asked to record lectures. So I started the recording on Zoom, so I hope to be able to then upload them somewhere after getting the video file. So you can, for future reference. The other thing is that I see here that there is a presence sheet, I think, signature.
Yes.
Okay. So I think you can sign that here you can sign it, and then I can take notes of people join. The other announcement is that on Friday there is no lecture.
No, right?
No, because it's public holiday in
Okay.
I don't know whether we're going to have a makeup lecture at some point. I'll ask and I'll let you know. Otherwise, we'll just go faster for the rest of the program. We'll let's say concentrate on things that are going to be more useful. Right? Maybe some things I'm going to leave some things as an exercise for you. Actually, I already have a couple of them for today, or actually for Friday. You can work on it. I'll highlight them in the class. Both, let's say, by hand and coding. So, what else? I think that's all. I guess. I'll note down this after the class. So first of all, do you have any questions about what we talked about last time? Something that was not clear, something that you would like to know more, or what about on Zoom? Can you still hear me, right? Can someone confirm?
Yes.
Ah, perfect. Any questions you have? Yes, George.
When we were talking about parkour, you talked about the angles between the parts, and the response of the robot was doing torques. Torques in that meaning is the idea of motion, right?
Yeah, torque
This
is
is a torque.
yeah, it's a force times a distance, right? Of from the axis, right? About which
Well,
this force
it's motion. It's the motion. Right?
Yeah. The physical motion is exactly that, right? So if you have an axis, in this case, it's the axis of the joint, which is this. Then a torque around this axis, right, is represented like I represent it like that, like a tau like that, which means it's a force times a distance on this axis. So this torque is exerted by the motors, the electric motors that have inside. It's something that is measured in Newton meters, for example, right? Just force times the distance. Right? Does that make sense?
Yeah. I'm confused because I learned that these type of motors only receive signals of angle.
Oh, that's yeah. So there are subsets, classes of motors that can be controlled directly in angle. You give a reference angle and they reach that angle. For example, the stepper motor, right? Which are specifically designed for controlling the position, so the angular positioning. Right? Whereas the general DC motors, the ones that you have for electric vehicles, on your washing machine, right? Everything, right? That has an electric motor. Typical electric motor is you give as an input a current, which is proportional to the torque. So it's just a scalar multiplication between the torque and the current. Basically, you give as input a torque, right? And you get as output an acceleration, angular acceleration, right? So that is what we didn't talk about last time. Like it was the last section of the first note, which we're talking about the dynamics of manipulation. And so the dynamic equation was something like that. Let's call it. Let's use the same notation of the notes. It was something like that. dq q double dot plus c q dot plus g tau. This is a balance of torques around each of the joints. Actually, this is a vector equation. Each component, right, is I know it like that, right? So the I component of this vector is the inertial torque. So this is you can think of the scalar version of this as m x double dot plus, have you seen this equation before? It's equal to a force. This is the then oscillator. Have you seen this kind of picture before? So here is an example of an oscillator. There's a mass attached to a spring, which is dead, like the temper that is in the suspensions of our cars. That's exactly what. And this is the equation that describes the motion of this kind of object, right? So you give as input a force, you pull this down, and as a result, you get an acceleration x double dot. Right, an acceleration in this direction, based on what the position and velocity of mass are. So this is the analogous. But as I was saying, it's a balance of torques. Each equation of this vector equation is a balance of torques around the ith joint. So the thing to remember is that for a manipulator, that's the block diagram version of it, right? We have as input tau 1, tau n, right, that we call tau. The vector tau. And as output, we have theta double dot, which is the acceleration of each of the joints. Now, what I said is that last time is that we will focus on models that do not take into account torques, which are called kinematic models, what we talked about last time, which is actually looking like that. So we give as input theta dot, right? Theta dot 1, theta dot 2, n. And we read as output theta. Right, this is what we call Q, the configuration of the manipulator. And this is what we call Q. So the picture is the same. Just that with this modeling choice, you give torques to the joints and read out the acceleration. With this modeling choice, you assume you can give velocity to the joints. So you can control directly the velocity of the motors, right? And give us output in angles. Which is, let's say, one derivative simpler than this case. Now you have no inertia. You assume that there is no inertia in this system. But actually, that's a good starting point to recap basically what we looked at last time. Let's do it. Let's do it. So we started looking at the concept of feedback control systems. Which look like this. We have a block representing the system that has inputs, which we call control inputs, and outputs. Then we said we would like this system to behave in a way that we want. Right? So what we do in order to do that, we close the loop with a control. This is a block. So inside here is an algorithm that takes as input the error between the difference, which we call the error between the reference and the measured output. So measured output is the value of the output as read by SC. Right? So we said our goal in this series of lectures is to design what's inside this robot. To make this system do what we want. In the case of the manipulator, we would like, for example, to pick an object, right, that is placed here with this gripper, right, this hand. So we need to control this manipulator to reach this position. So that's the behavior that we would like the robot to execute. So how do we control? How do we choose, in this case, the velocity to give to the joints in such a way that this moves this way? Okay. So this is the idea. To do that, we said let's use a model for the system. System models that we looked at are manipulators. Manipulators, we looked at the kinematic, differential kinematic model, right? Which is the x dot, I think x e dot, the pose of the end effector equal to j of q times q dot. What are these elements here? So x e dot is the position or the pose of this point, which is for the end effector. Q dot, Q is the vector of, in this case, it's the set of variables that describe the configuration of the robot. Right? So we call this Q1, this Q2, this Q3, and Q is the collection of Q1, Q2, and Q3. And J is the so-called Jacobian. The Jacobian is has this name because it's actually the Jacobian of a function, which is the forward kinematic function. So starting from x e equal to f of q, j of q is defined as e f e f. And last time we saw the dimensions that this has based on the dimensions of q dot and x e dot. It's a matrix in the general. This is for manipulators. For mobile robots, there is an analogous equation to this differential kinematics, which reads like that. In that case, q dot is equal to g of q times u. So the example that we had last time was for unicycle. Let me draw it here. Is this triangle that has the ability to move, to rotate, and translate on this plane. And its position in this plane is denoted by the coordinates x and y, and its orientation is theta. So the configuration in this game vectors x, y, theta. The collection of these three numbers that we need to define the poles of this and of this problem. And the U, which is the control input, is what we call V and omega, the longitudinal and angular velocity of this problem. This is V, velocity, it's a speed in the longitudinal direction, and this is omega. It's a speed around the axis, right, orthogonal to the plane in which this problem. So the steering speed. Yeah. Right, so these are the control input. This is the control input. And this equation, in the case of the unicycle, we said we saw things like this. So we have q dot equal to x dot y dot omega dot is equal to p cosine theta b cosine theta omega, which can be written as cosine theta sine theta 0 0 0 1. And then we have B omega. Right? So this is the G that when we explicitly say that depends on money. And here is the and we saw a simulation last time, right? Where we give as inputs this V and omega, different combinations of V and omega, and we see how the robot moves. So x dot, y dot, theta dot, how they are evolving in right? So these two key equations, which are the kinematic models of manipulators and mobile robots that we use, are what we can think, is hidden in this system block. Right? So for the rest of the class, the examples that we will make for manipulators, we have as input q dot. So the system block for manipulator will be like that. This is our modeling choice, right? So that's our choice of a model for the manipulator. We give as input velocity of the joint. We need as output velocity of the end effector. Whereas for the unicycle, or for the mobile robots, particularly for the unicycle in this case, the system block will have as input U, what we call the control input for the mobile robot, and as output, that is our modeling choice. That is useful for what we are going to do. Obviously, it's not a universally good choice, right? As we said, models are good for a reason. It's not that they are the ground truth, right, of our system. Because remember, all models are in a way wrong to some extent, right? Because they neglect some effects. In this case, we are neglecting the inertia. You're saying, no, I don't care about modeling that aspect. I just want to know the behavior from joint velocities to end effector velocity. So that's the summary, let's say, of what we saw last. Any more questions or doubts on this? Yes, someone spoke on Zoom.
No, I said that there are no questions.
Good, thanks. All right, if not, let's figure out what to put inside this control. As we said, or as the title also of this course says, we are interested in designing controllers which are based on optimization. Why? First of all, because the language of optimization, as we will see, is very natural to express different different, let's say, objectives, right, that we want our system to fulfill. The other two important things are that first there is a well-developed theoretical and computational framework to solve this kind of optimization problems that will show up in the evaluation of the project. And the third thing, which is extremely important, right, that in a way justifies the success of these controllers, is that we have the computational power on board of most robotic systems nowadays to solve optimization problem inside this component. So in the past, it was not possible because of computational complexity, right, to solve an optimization problem inside this block that runs inside this control loop. Nowadays, it is possible, and since optimization has these advantages, why not use it in the control loop? So let's see what an optimization problem is and what can we do with it, right? With robots. Is any of you familiar with optimization theory or how to solve an optimization problem? What is an optimization problem?
I have studied a little optimization applied to data science, and we have studied some
Applied to
data science.
Ah, okay, sure, yeah.
Some algorithms.
That's right. So the optimization is all over the place, right? In machine learning and data science, because obviously you're looking for something that is optimal, right, with respect to some cost and based on data, right? So in fact, I think today we're going to look at an algorithm which is used all over the place in data science to solve optimization problems. All right, let's start with the unconstrained optimization. So in an unconstrained optimization problem, what we are going to do, or our goal is to pick a decision variable such that a cost function is minimized. That's it. That is written as follows. Minimize G or U over U. So U, which we're going to say is a vector in Rm, is our decision variable. G, the function that maps from Rm to R, it is a scalar G of U, is cost. So for the purposes of designing a controller, we will assume that G is continuously differential. C1 is the set of continuously differentiable functions. You can take derivatives and they're continuous and everything is nice. So how do we solve this problem? For now, it makes sense, right? It's very close to into English, the English words like minimize a cost, like over a variable. But how do we do that? Right? So the first notion that we need to figure out the solution is that of a minimizer of G of U. Minimizer, which we call U star. Right? the optimal variables are going to be denoted by any star. So minimizer of G of U is a vector behind U star. Is such that the G of U star is less than G of less than or equal to G of U for all U in a delta ball around U star. P delta here is the set of D in Rn, which are delta away from U star. The open ball delta. So in particular, since this is a notion that is based only on a neighborhood, like an open ball around U star, this is also known as a local neighborhood. So we are not, in a way, defining this U star to be less than G of U for all U, possible U, but just in a neighborhood around U star. Right? I just looking locally, that's why it's called local. The picture, right, is the following. We have a U star here, so there is some delta here, such that all points that are inside here, all the U's that are here, yield a cost, which is not smaller than G star. To make sense as a definition. So the interesting thing is that there is some necessary condition for U star to be a minimizer. A local. Which can be used. So a necessary condition for U star to be minimizer. The gradient in GBU evaluated at U star is 0. Right? I guess I mean you kind of imagine that when you calculate the maximum and minimum, right? Or other critical points, you start from this. This is literally a necessary condition. Right? Why is that? So if you expand G and U star, expand G of U, right, around this point in a ball around U star, then you can write it like that. Plus epsilon U and u star p plus higher order terms. So terms that have derivatives higher order than the first. Right? What are these epsilon and these? So epsilon and b, if we look at this picture here, this is b, a vector of unit norm, and this is epsilon b. So epsilon is a scalar for epsilon greater than 0, b in Rn with unit norm, such that epsilon b u star plus epsilon b is in with b delta u star. So it's just another way to express points which are close by. Right? We start by subdividing them into the direction b and the magnitude epsilon. So now the thing is, we're looking at this necessary condition, right? So if this is not 0, this one, assume this one is not 0, then we can pick b equal to minus g u and u star transpose. This is a vector in Rn, right? And get that g of u is equal to g u star minus epsilon g u and u star g u and u star plus I am. This one is the norm of this gradient. Whatever. So it's positive. This epsilon we said is positive. So for epsilon goes to 0, this term disappears, and gu g of u is less than gu star, right? Which is a contradiction, right? Or u star to be a not assumption that you start. So this is a necessary condition. Fine. Two things to note about this derivation or this condition are that first of all, it's just necessary. That means that if the gradient is 0, you're not sure that we cannot conclude that this is a minimizer, right? As we know from calculus, right, it could be a maximizer or a subtle point, right? Depending on some other condition. The second important thing is that looking at this derivation, we can actually design an algorithm to minimize G of U, which is literally this. So if you want to minimize G of U, all we need to do is to go in the direction of the negative gradient. Right? Because this gives values of G which are less than the point where we started at, you started. So the algorithm, so this is a numerical algorithm. Let's see, minimize G of U. based on that is the following. So initialize U0, right? And initialize U0 somewhere. Initialize k to 0. Initialize the parameter alpha greater than 0, which we're going to use. And then what you do is, while the norm of the gradient at UK is greater than a value delta, or you also need a delta here. Okay. We do is UK plus 1 is UK minus alpha times dGdu UK alpha. And then k is equal to k plus 1. So delta here is a threshold. Let's say a convergence, we call it threshold. Alpha is a step size. Data science, this is called the learning rate. So what we are saying in this algorithm is that until we get the point that the gradient is less than a desired threshold, what we do is to move in the direction of the negative gradient, right? Which is going to bring us to the minimum. And the proof is very similar to that derivation that we used to prove that there is a necessary condition, right? The intuition is very simple. If there is a gradient that is non-zero, right, that we are not at a minimizer, that's the positive, right, of that necessary condition. Which means we can move in the direction of the negative gradient to decrease the cost, right? So, intuitively makes sense. So you see, in I don't know, 10 minutes, we went to write in an optimization program that didn't make any sense, right? Unless, I mean, besides the English words, right? To an algorithm to solve that, right? So it's as simple in a way. And I think at this point, I can also show you how this optimization program will be run in code. So the lecture notes are updated, right, with the second lecture, and inside those notes you can find the link to the Google Colab related to optimization, where there are, let's say, pieces of code that I've used for run these algorithms. And in the meanwhile that I turn this on and share the screen, let me know if you have any questions. No questions? No. All right, so this is the example of the unconstrained optimization, for which In this case, we are barely using any library. Literally, yeah, we're using just the plot library, shootings. Nothing else, right? And we are implementing this algorithm. So we want to minimize a function like that. We want to minimize a function like this, right? So this is a cubic, whatever function, which we define here as an inline function, and we also compute the gradient dg on this function. We initialize some values like this. This is the alpha, the step size, and the u, right, which is our first function. So this case is the case where m is equal to 1. So the cost is a scalar function of a scalar. The optimization variable is a scalar. So right, so everything is a scalar. The only thing we do here is in this step function is to substitute u with u minus alpha times the gradient. If we run this again, here is still connected to the online resources, but the majority of the time is spent to create the animation. It takes no time, and it's just matrix. In this case, scalar multiplication. One line of scalar multiplication. In the multi-dimensional case, it's still a matrix multiplication, so nothing. Nothing that it could. Once it creates the animation, so we see that we initialize our u at 5 here is about this much, and running the gradient down the gradient, we reach the local minimizer. So this by no means is the global minimizer. Global minimizer is somewhere at minus infinity here. But we reach a local. If initialize the u to be somewhere else, at minus 5 in this case, which is on the opposite side of this pole, right? We still reach the same local minimum, which is at 0, yeah, at 0 in this case. We try to initialize this further to the left, right? Minus 8 in this case, which is somewhere here, right, on the left of this bump. Then the gradient, right, is pointing this way, it's pointing to the left. The gradient is negative, right? Sorry, the gradient is positive, minus the gradient is negative. So we go to the left. And if we try to run this, I think it should not even finish the animation, yeah, because it says, yeah, numerical results out of range is going to minus 3. Right? So this algorithm, since the way it is designed, since we're moving in the direction of the negative gradient, it's called the steepest descent algorithm. Because we are descending the cost in the direction of the steepest descent. The way rivers do, right, on mountains. That's exactly the same algorithm. They are running the same algorithm. But the nice thing is that exactly the same algorithm works for multidimensional decision variables. In this case, we have a u that is 2-dimensional, and we want to minimize this kind of function. So u1 and u2 are the first and second component of the vector, 2-dimensional vector u. G of u evaluates like that. So this is the function, and this is the gradient. Now the gradient is a 2-dimensional vector, right? That tells us the direction of in which the function increases the most in the x and y, right, components. And here we choose again different alpha. Here I chose a much smaller alpha just to see because to see the update, otherwise it's not even faster. Converge, and majority of the code is to plot the function. And if we run this, which is again exactly the same as before, the only difference is the way we plot two-dimensional functions. Sorry, functions of two-dimensional variable, which looks like this. Right? So here we see the contour plot, right, of the function g, with this in the level sets, right? Or yeah, or this function, and we initialize u to be at 4,3 somewhere here. So that going in the direction of the gradient in this kind of motion. Right, so it goes, the gradient is orthogonal to the level curves, right? This is something useful to know. So we're going this way, and then we are curving to 0, 0, 1, I think, or 0, 0.5, yeah, somewhere there. Now, in the same way, we can try to start from different initial conditions. So in this case, we start from -3, 2, which is on the left of what we saw. And we are converging still to the same case, still to this point. So this is not by chance. Because if G is convex, then a local minimizer is also the I stress that is unique global minimum. Have you heard of convex functions? Voice.
I think I heard I know the definition.
The definition is very simple. Pictorially, convex function looks like that.
I'm sorry, Professor. You said convex sets.
Convex function. So G is a convex function, which is a function, right? So you see,
Okay.
right, have you heard of convex functions, right? So this is a real function of a real variable, which is convex. It's a ball, which tells everything actually about the convexity definition, right? Because the definition of a convex function is the following. If we take, so this is a G of U. So if we take 2 points, any 2 points, U1 and U2, and then we draw the line segment that connects U1 to U2, and this line segment is above the function. That's the definition of convex. Which in mathematical terms means that G of alpha U1 plus 1 minus alpha U2 is less than or equal to alpha G of U1 plus 1 minus alpha G of U2. That's the whole thing. Exactly the same, like the segment is above. Why? Because this term represents a point. So let's call this alpha U1 plus 1 minus alpha. So this is this point. And this is this point. And this has to hold for all, as I said, U1, U2 in Rn, and for all alpha in 0, 1, which means not only a point in between, but all points in between U1 and U2 have to have this, have to satisfy this condition, which means the whole segment is above the function. Does that make sense?
Yes.
So the important thing is that if G is convex, then it doesn't matter where we start. We're going to end up always at the same point, which is the global geometry that is unique. So this is why when we initialize this at different points, right, it doesn't matter where we start. We're always going to end up in the same place because this G is a convex function. And you can somehow figure out how that G looks from the contour plot, right? So these are the level sets, these are the contour lines, right? So it looks like a ball, like a ellipsoidal ball. Right? So no matter where we start, this little ball, right, we get running, it's going to end up at the unique global. Now, the interesting thing is that okay. Let's do yeah, let's do a let's get rid of this project. Let's say a few more words about this convex optimization program. So specifically, the one that we have looked at was minimized over U. Actually, let's read it exactly as it is. Is 2U1 squared 2U1 squared plus U1 U2 plus U2 squared. Minus 2U1. This is a quadratic curve. So what quadratic terms in the vector U, right, are basically made of terms which look like squared components of U, multiplication between two components, any two components of U, and linear terms. In general, they look like that. The U transpose U plus B transpose U, where Q is a symmetric and positive definite function. Do you know? Have you heard of positive definite matrix? Sorry, matrix. Have you heard of positive definite matrices? So basically, this term is always positive. That's what it means. And P is just a vector in Rn. Right, so how do we express this in this form? Where Q is a symmetric positive definite matrix and P is a vector. So how do we go from here to here? So we can have Q to be, so it has to be 2 by 2 matrix because it multiplies a 2 by 1 vector, right? On the left and the right. It has to have a 2 here, which gives this term. And a 1 here, gives this other term. And then to get U1, U2 in a symmetric way, we can have 1/2 here and 1/2. Do you see why? You can try to do this. U transpose Q. You see that this matches this. And then there's the other term, which is very easily to get from here. So P is -2. Right. So that when we do this scalar multiplication, right? P transpose U is in the product, right? Between P and U to get -2 U. So this is the general version of a optimization problem where the boss is quadratic. And optimization problems where the cost is quadratic are an instance of a so-called, not surprisingly, quadratic problem. For which there are libraries to solve in any programming language. They are very efficient, and that's actually what we're going to use in most of the controllers that we derive in this lecture, in the future lecture. There's an example before we look at the code. So minimize for U. This U transpose to U minus U transpose U, where this is symmetric and definite, this is the vector in Rm. So how do we find the minimizer? So to be a minimizer, we need the necessary condition, which is the G of the U at U star has to be 0. What is the GDU? This is G of U, right? What is the GDU? Partial derivative of this term.
Is the gradient.
Yeah, that's the transpose of the gradient. But yeah, sure, the gradient.
Okay.
What is the gradient of this term?
To be 2QU.
Right? So this is transpose of that. So 2U transpose Q.
Okay.
Should be Q transpose here, but Q is the same as Q transpose. And of this is minus B transpose. Right, that's easy, right? Whatever is in front of you, we write it here. This one requires some more thought, but dimensions make sense, right? P transpose is a row vector. U transpose Q again is a row vector. So they add up in a nice way. So this has to be 0. For U star would be a minimizer. So U star is equal to 1/2 Q inverse P. Right? This is required for U star to be a minimizer. Now, is U star a minimizer? Could be a maximizer, as you said, could be a saddle point. Now, the sufficient condition, well, first of all, we said if the cost G is convex, then the minimizer is the unique global minimizer. It's actually a minimizer, and it's the only one. Now, the sufficient condition for G to be convex is that the second derivative, E squared G U squared at U is positive definite. That's strictly convex, that is convex. For all U, in Rn. So this implies G is convex. Very useful condition, right? Sufficient. So we can, in a way, figure out whether this G of U is convex or not. What is D squared G du squared? So we need to differentiate this one once more with respect to U. The only term that depends on U is this. Then the derivative with respect to U star, with respect to U is 2Q. Now, 2Q, since we assume that Q is positive derivative, for all U, there is no dependence on U, it's constant, right? The second derivative. So G is convex, which means that this is the global minimizer. A very unique, just to stress again point. That is the unique global minimizer. In this case, quadratic programs are very useful or very convenient to have, because we can easily find the best of the best solution. Unique global minimizer.
Professor, since we are dealing basically with the solution of a linear system, we could actually make a preconditioner, apply a preconditioner to the problem.
What do you mean by a linear system?
Because when you differentiate it, you just get 2u q minus b, and actually for finding the u that minimizes, you have to solve this linear system.
Sure, linear system equations, yes. Then you're saying you want to make the cost quadratic and convex?
No, just what I wanted to do was just transform the Q matrix for it to be to actually shape in a way to maybe have a better convergence rate or anything like that. I'm just thinking of using a conjugate gradient to solve this system.
If you want to use a numerical method, yes, to go to the U star, to reach the U star, then yes, you may want to resort to this kind of algorithm. In this case, we are not using any numeric method, right? We are finding the right solution in one shot, in one matrix multiplication. So there is no numerical algorithm to find it.
Okay.
But in that sense, you're right. If this is not as simple, we will see examples where you have also constraints. So it's not just that minimize a cost, but it's minimize a cost subject to some constraints. Then yes, you will need to resort to these algorithms, and your suggestion I think would be useful in the numerical algorithm.
Yeah. Thank you.
But yeah, let me know if you have more questions. We can talk more about these things offline. Okay. Okay, so now I think let's I think I leave this as an exercise, but it's very similar to this example that we solved. And you can try to solve it on Friday, for example, or between now and Monday. And let's also write code for it based on what we will see on Google Colab. So the exercise is the following. Minimize over Q dot J Q dot minus X E dot norm squared. Now X E dot is a vector in R. What do we call it? RR, the dimension of the task space. Q dot is a vector in Rn. So J is a matrix in R cross N, and we will assume that in this case, N is less than or equal to R. So we have less degrees of freedom, less controlled inputs to dot. Then task variables, XE, the dimension of XE. So the Q dot star solution of this exercise is actually the inverse kinematic solution for a manipulator that has less degrees of freedom compared to the task variables. This is an important thing to remember. We didn't talk about inverse kinematics algorithms or what do we need to do, right, to solve for a Q given an XE, right? This actually is the solution. Q dot star, right, is used to solve the inverse kinematic problem. Inverse kinematic problem with n less than or equal to R. So I think I have these in the notes. Yes, this is actually solved in the notes. But you're encouraged to try it yourself. The first thing you should know is that these two are very similar, are actually the same. They are the same optimization problem. This norm sounds a little weird, right? I mean, here we don't have any norm. But if you expand this term, you will get a quadratic term like that. So the first step would be to do J Q dot minus XE dot transpose times J Q dot minus x in dot. Right? And here you will get a quadratic term like that, where u is q dot in this case. A linear term like that. Additionally, you will also have a constant term, which is only a function of xc dot. So xc dot is not a optimization variable, it's just numbers, it's a vector that we already have, we already know. So it's not an optimization variable, so you can drop it for the cost. But let's write it down. This is something like that, right? We have minus 2xe dot plus j dot, and then plus xe dot transpose xe dot. So this is our quadratic cost, quadratic term of the cost. This is the linear term, like linear in q dot, and this is a constant, right? It doesn't depend on the q dot. So no matter what q dot you choose, that term is always going to remain constant. So you can drop it from the cost. Minimizing this is the same as minimizing this. Right? In this example, for example, this solution, what is that? No, we didn't solve it. But this, right? Yeah, whatever. This solution is the same as if here I put plus 3. Right? It doesn't matter. The minimizer is always going to be that. Yeah, something like that. Because when we take the first derivative, this term disappears. So once you transform the cost like that, then you should be able to write down a solution straightforwardly, right? Using this for that. And going back to the question of Monday, right, that some of you had, I think, on Zoom, is about the invertibility, right, of J to solve the something related to inverting J. If it is not squared, then we need to invert it, right? This is the solution to that, or it is an answer to that question. You will see that somehow you need to invert J transpose J, right, which is your Q. So what you're gonna get as a solution is the pseudo inverse of J. And if n is equal to R and J is invertible, then the pseudo inverse is the inverse. I'll leave you figure this out. If you have any question on this, please let me know. I'll be responding I'll be responsive on Friday or tomorrow, or any day. Do you have any questions about unconstrained optimization or convex functions or quadratic robots?
No problems.
Cool. In that case, I'll show you how to solve. So the same program, this same optimization program that we solved numerically by using the quadratic program solver. Let's share screen here. No. So here is where we were before, right? So we wrote this algorithm, which is the steepest descent to find the optimal solution. Now what we're gonna do is to use a solver to solve this. And since this is a QP, we're gonna use one of the QP solvers for Python, available for Python. This is in the QP solvers package, and it's called the function is called solve QP. And to install that, you just run this at the beginning. So this installs the QP solver package in this Google Colab, which then you can use functions from. And I put also a link to the documentation. Right, so here you can see also an example. You have this prototypical optimization program. It also has constraints. For now, we will not talk about constraints. But basically, you need to give as input P and Q, and it will give you the optimal solution X. In this case. So in our case, let's go back to this, right? So in our case, B, right? Let's use the same term, right? It is Q, right? This matrix Q is 2, 1/2, 1/2, 1. So here is times 2, just because the way this function accepts inputs, right? Because B is 3 multiplied by 1/2. So we just need to give a 2 in front of Q to get the same expression of Q. And this is what we call the P vector. No, P vector is minus 2, 0. So here we have the function that solves for us this optimization program with the Q matrix P vector. And here you need to decide what solver you want to use. In this case, it's called solve. And it did solve the optimization problem, and here we print it. And what we're going to do is to plot this solution UQP, right, on the same figure where we solve for the optimal solution using this steepest descent algorithm. So here the cross is the solution obtained using solve QP function, and this dot is the outcome of our steepest descent algorithm. Right. So it's as I was saying, you are encouraged to write a program to solve that optimization program using this solve QP. I think I wrote it also at the end of this as an exercise. You can solve the inverse kinematic problems, right, for manipulators with the n less than r using this solve QP for unconstrained quadratic problem. That's it. Question about this? All right. So if not, in the last part of this lecture, we'll talk about constraint optimization, right? So the goal now was to pick any U in Rm to minimize a cost. So we were in a way unconstrained to choose a vector in the whole space, the whole Rm. Now we're going to see what happens if we have constraints. So minimize U over U, the function, the cost function G of U, subject to H of U equal to 0. This is an equality. And the function H is a function that maps from Rm, so dimension of U, to R K. Right, so we have K equations. The picture in 2 dimensions. Is actually like that. So let's assume m is equal to 2. So this is R2. At each point, there is a value of G, right? And then H of U equals 0. Let's assume K is equal to 1. Right, we have only one constraint. Is the following. So we have a curve which represents all points in R2 where H is 0. So on this side of this curve, let's assume H is positive. On this side is the H is negative. So if you want to minimize G of U subject to H of U equals 0, what we need to do is to search along this line for the optimal. And what are the conditions or the situation, right, for which in which a point U might be optimal? So there is so first of all the U that are on H equals 0 are called feasible U because they satisfy this constraint. So among the feasible U, there might be U's like here, 1, where the gradient points this direction. This is U1 star, BGBU, and U1 star. And this is the case of an optimal solution, U1 star. Why is that? Because the gradient BGBU is orthogonal to the tangent in H. Why is that? Why should that be the case? Because if the gradient was not orthogonal, say it was pointing this way, right? We could move along this line, or actually along the opposite direction, right, of this line, and decrease the cost. Just like we did for the unconstrained case. It's just that here we need to project the way this gradient onto the tangent with this line. But if the gradient is not orthogonal to the tangent, we have room to move. Right? There are points in this ball, right, around U1 star, which is a lower cost, particularly some points on this line. Right? So this is one situation for which U is an optimal, is a solution of this. The other obvious case is where, for example, U2 star and BGDU at U2 star is equal to 0. So if the gradient is equal to 0, then yeah, of course, it's a solution because around it there are no points that are better. So in this case, no points in this ball are better than U star. So if the cost is lower than G3 of U star. In this case, it's not true that no points around U1 star in the lower cost. But these points are not feasible because we should move away from U equals 0. Right? You see this concept? It's like oh yeah, it's like for a river that is going down the mountain, right? If you put a wall That's a constraint. So that the optimal position, right, for a lake in that case would be the position where the wall is. Because the wall is a constraint, we cannot move past the wall. So that point is the best, right? We can achieve subject to we stay where the wall is. We should move past the wall to be better, but that's not easy. That's the idea. So how is this represented in a way? Or how it can be represented in mathematical terms? So we said that the gradient has to be, the gradient of G and U star has to be orthogonal to the constraint function H equals 0. Now, a thing to know is that, as we said before, the H, du, and U is orthogonal to the tangent H and U. So this is H equals 0. This is the tangent. This is the gradient. The H U. This is a fact, but it's not difficult to show. It's the same thing that we said before, right? The gradient is orthogonal to the level curves. That's what is. So the condition of G, U, and U star being orthogonal to the tangent, right, is the same as saying that DG, DU is parallel to the HDU. Right? So orthogonal to the tangent means parallel to the orthogonal to the tangent. Right? So this would be DHDU and U1 star. Because H is growing this way. It's growing from 0 to positive, going down. The important thing is that that's orthogonal. So how can we say that two vectors are orthogonal? No, sorry, that vectors are parallel. We just say that they have a scalar multiplication. They're just a scalar multiplication away from each other. So they are, for example, let's call it minus lambda dh du star transpose, or lambda, for lambda in R, whatever sign it is, which is the same as saying that dg du and U star transpose plus lambda dh du U star transpose is equal to 0. Just brought it on the other side, which is the same as, can you read it here? D du of G U star plus lambda H U star is equal to 0. So this geometric condition that says that the gradient of the GDU has to be orthogonal to the tangent to the line H U 0 is the same as saying that the derivative to the gradient with respect to U of G plus lambda H evaluated at U star has to be 0. Does that sound familiar? Have you seen these kind of things before?
Yeah, that's Lagrange multipliers, isn't it?
Exactly. So this lambda is, I mean, I think somewhere else. It's the in general, actually. So this was the picture that we could draw because we had this m is equal to 2, k is equal to 1, everything is in the plane. But in general, the same thing happens for a generic m and q. What do you see? K and n arbitrary. Same thing happens. So d u of g u star plus lambda transpose, because now lambda is a vector in R K, has to be equal to 0. Now, this function g of u plus lambda transpose h of u is defined as the Lagrange. This is called the Lagrange. And it's a function of u and lambda. And lambda is called the Lagrange multiplier. That multiplies the constant. So now you see the interesting thing is that we went from a constrained optimization program there, minimize g subject to h, to an unconstrained optimization program, where the cost here is different. Now the cost is g plus lambda transpose h. But there are no constraints. There is an additional variable, lambda, but there are no constraints. So that's the interesting point of using this formulation, right, to solve constrained optimization problems. So in the end, how do we solve this constrained optimization? By just solving a simple system of equation. U star is a solution to this. If there exists a lambda star in R K, such that the L U star, the L B U evaluated at U star lambda star is equal to 0, and the L B lambda evaluated at U star lambda star is equal to 0. Where L of U lambda is equal to G plus lambda transpose H. So before we were doing without the constraint, we were just saying this is a solution if the GDU is equal to 0. Now with the constraint, we're saying U star is a solution if the LU and the LD lambda are 0. And by the way, this the LD lambda, this is equivalent to H at U star. It's nothing but that. Because the derivative of L with respect to lambda is H. This is just saying the U star should satisfy the constraint. And this one is this condition. Questions about this? Now we're gonna do an example where we are going to solve the same quadratic problem as before, but with some constraints. Or a quadratic problem minus plus. Let's see. Can I get rid of this? So the example is as follows. Minimize the norm of U squared over U subject to A U is equal to B, where A is a K times N matrix. The rank A is less than N. The rank of A is maximum is A. And B is in the range of A. Have you heard of the range space? Oh, sorry, the range of A, the column space. The range. You have the null space and the range space. Our matrix. So the range space is basically the set of all vectors here in R what we have here K, such that there exists a doubling in R N such that A doubling equal to. So it's a vector that you can obtain by multiplying another vector by A. Right, something in the image. This condition basically makes this constraint visible in a way, because if B is not in the range of A, there is no U that you can pick, such that AU is equal to B. So if this is not in the range, this does not make sense. The so-called feasible set is empty. So the set of all feasible is empty. So I will solve it. Just write down this system of equations, for which we need the Lagrange, which is U squared plus lambda transpose. Now this H. What is our H of U? Not right times AU will equal B. But then we can write that this form by defining H as AU. This is the same as AU minus B equals B. This is our H. So we have the Lagrange. So now we write down the gradients derivative with respect to U at U star lambda star, which is 2 U star transpose plus lambda star transpose A equal 0. And the other one is the constraint that we said. It's A U star minus B. So from here we can figure out what U star is in terms of lambda, which is minus 1/2 A transpose lambda star. Then we can plug in here, getting minus 1/2 A transpose lambda star equal B. From which we can figure out lambda star is equal to minus 2 A transpose inverse B. And this exists, this inverse exists because A has full rank. So A transpose is a K by K matrix, which has K dimensional space. We can keep it and get lambda star, which then we can easily substitute here to get U star equal to A transpose A transpose B. This is also called the right pseudo inverse of A. And we're done, right? So this is the optimal solution to this constraint optimization problem. It was as easy as to solve this kind of system equations. Is that clear? Or do you have any doubts or questions on this procedure? If not, a second exercise would be minimize the norm of Q dot squared over Q dot subject to J Q dot equal X E dot. But now J, so XE is always a vector in R. I think this is in R. Q is in Rn. So J is the usual matrix in R cross N. But now N is greater than or equal to R. then equal to bound. So we have more degrees of freedom to pick for joints with our manipulator than pass variable. This is the case of the so-called redundant manipulators. They have more degrees of freedom than the ones required to solve tasks. And again, this is exactly the same as this. Now the parallel is even more apparent, right? So just naming U as Q dot, A as J, and B as X dot. So with this, you are solving the inverse kinematic problem of redundant manipulators. Or this is a piece of the solution of the inverse kinematic problem of redundant manipulators. Okay. So last thing that I wanted to talk about is when we have inequality constraints instead of equality constraints. Right, but I leave you to read, let's say, the theoretical derivation. We just look at the implementation here. But it's very similar to what we saw for the inequality constraints, like how to find the necessary conditions for optimal points, optimal solutions of constraint optimization with inequality constraints. The picture is very similar. Yes. Since we are not going to solve anyway these problems, in particular the one with the inequality constraint by hand, because they get much more involved than the equality constraints, we can just state how they look. So h of u in this case is less than or equal to, when this is this less than or equal is component wise. So for each component of h of u, there are k components that we have this inequality. In the particular case of a quadratic program, which is usually for QP, this constraint optimization to complete a quadratic program looks like that. U transpose U plus A transpose U subject to, we have G U less than or equal to H, A U equal to. So this is the whole picture, right? This is a quadratic cost. And these are so-called affine constraints. Which are basically linear in U plus there is also constant. That's the affine. So with this in mind, then we can solve this kind of optimization problems, and using the same function, the QP solver that we saw before. but this time is for a complete quadratic problem. Let's see. There we go. How the mark is substituted by code, like literally 1 to 1 in this case. So we have the case of equality constraints, right? So the same problem as before, P and Q are the same. But now we're saying, let's make U1 equal to U2. So the two components of U have to be the same for some reason. So we can write that in the form A U equal B, but just defining A as 1 minus 1, row vector, and B equals 0. So when we do this multiplication, we get U1 equal to U2. And we input this A and B in the solve_QP function. So the solve_QP function, as we saw, takes a bunch of arguments. In order they are P, Q, G, H, A, and B. And then there might be others as well. So here we have to have P, Q, none for G and H, because we have no inequality constraints, and A and B for the equality constraints. And when we solve this, now there is no time to wait, right? Because this is solved instantaneously. There is no animation to be done. The contour plots are the same because the cost function is the same. The constraint line in this case is this black one. So this is where x1 is equal, the u1 is equal to u2. And the optimal point is this red cross, which makes sense, right? Because in a way is the closest point to the optimal here, measured right as the by the value of the cost, right? That is on this black line. Yeah, I think if we have 2 minus 1, we have different inclinations for this line, but is all the same idea. Either you get the closest point, again measured by the cost function, to the optimal, to the unconstrained. For the inequality constraints, it's very similar. Here, for example, we say, let's assume we want to find the optimum such that U2 is less than or equal to 1. Right, so we want to search in the space that is under the line 1, right, of U2. And which is this. And here it is. So actually, under the line, so U2 has to be less than 1. The unconstrained optimum point is also the constrained optimum point, right? So we actually get the global minimizer. If we push this line down, right? If we push this line towards, I don't know, -1 instead of 1, so here is -1. Then we are bringing down, pulling down the optimum, which tries to go, as the example of the lever I was saying before, tries to go to the unconstrained optimum, but it stops here because of the constraint. And I mean, with this, you can basically model all sorts of affine constraints, right? That it can like different, but the idea is this. Right, so I'll leave you play with this code also to solve the quadratic program, right? With equality constraints that for the inverse kinematic problem or for the proper manipulator problem there. Using the equality, and then you can experiment with the more inequality. In fact, from next week, so Friday there is no class, right? For next week, we are going to use, in particular, the inequality constraint quadratic programs to design a custom program for robotic systems. That's going to be for manipulator or and mobile robot at the same, in the same way. All right. So again, if you have any question in the meantime on these examples, exercise, code, if something doesn't work, let me know. By email, I'll be available. And I wish you a nice weekend. All right, I'll see you on Monday. Gravação means recording because